This is Common Core State Standard Support video for mathematics. The standard is 5.nf.5b. This standard reads, interpret multiplication as scaling or resizing by explaining why multiplying a given number by a fraction greater than 1 results in a product greater than the given number. Recognizing multiplication by whole numbers greater than 1 is a familiar case. Explaining why multiplying a given number by a fraction less than 1 results in a product smaller than the given number. And relating the principle of fraction equivalence, a over b is equal to open parentheses n times a close parentheses divided by open parentheses n times b close parentheses to the effect of multiplying a over b by 1. Now the key idea is the opening statement, interpret multiplication as scaling or resizing. Now when we multiply some given number by a fraction, that fraction is actually the scale factor that's going to change our original number. Now one of the things that isn't explicit is that with any fraction like here a over b, the denominator cannot be 0. So in all of these instances b cannot be 0. The first part deals with multiplying some number by a fraction that's greater than 1. The second part of this standard deals with multiplying some number by a fraction that's less than 1. We have to look at the big picture here, and when we look at these variables, we need to understand that the numbers that we're dealing here are positive because integers are not covered until grade 6. So here, all of the numbers that we're dealing with are positive. So, for example, when we talk about a fraction being less than 1, we're really talking about a fraction that's between 0 and 1. It's a proper fraction that's positive. Now, there is a third context where our fraction could be equal to 1. Even though they're different letters, different variables, there's nothing that prevents a from being, say, a 7 and b also being a 7, which of course would be 1. Now, let's look at this idea where the fraction would be equal to 1. Now, what we need to realize is that that idea does not come from that last statement in the standard. That last statement in the standard is actually not related to those first two. And so what we'll do is we'll worry about the third statement in the standard and address it at the end. Now, any fraction can only be equal to 1 if we're talking about the numerator and the denominator being the same number. So in this case, a over b can be 1 only if a is equal to b. And for the purposes of this video, from this point onward, we'll just refer to this context where the number would be times 1, like so. Now, this third possibility where the fraction is equal to 1, that's important because that's going to be our benchmark for comparison. Also, when we look at these two scenarios where we have fractions either larger than 1 or smaller than 1, there's two necessary understandings to make sure that we're all on the same page. First of all, when we're talking about multiplying, we're going to interpret the multiplication where the first factor tells us the number of the sets or groups, and the second factor is going to tell us the size of each set or each group. Now, the standard talks about comparing to a given number, okay, and we'll just call it n. If we take that number and multiply by 1, it doesn't change. You know, that's the multiplicative identity. Also, if we start off with some number n, it's understood even without context based on place value that that's so many ones. So that's a second item that connects us to this idea of n times 1. And then the third thing that would connect to n times 1 would be that third possibility where the fraction a over b could be equal to 1. But the main reason that we need to look at this number as something times 1 is that it's necessary for it to be in this form in order to physically model the comparisons. And that's the key reason for our number being something times 1. So let's look at the first scenario where we're going to multiply some number by a fraction that's larger than 1. So we start off with our given number, and we're going to multiply by some fraction that's larger than 1. And for comparison purposes, we're going to think of our number as something times 1. And let's let our fraction that's bigger than 1 be 3 over 2. We could pick just any number that we wanted, but for simplicity, let's start with our number being 3. So what does this look like? 3 times 1 versus 3 times 3 over 2. Well, 3 times 1 means that we have 3 sets of 1. And on the right, well, wait a minute, that's just 3 sets of 1. That's not enough. Oops, now this is 3 sets of 2. That's too much. So what we need to do is we need halves. So we need to take our sets on the right and cut all of those in half. And so now we have what we need. We have 3 sets of 3 halves in each one. So here's one of the sets. Here's a second set of 3 over 2 and a third set of 3 over 2. Now just using logic, on the left we see that we have 3 sets of 1 compared to 3 sets of 3 halves. So we know that 3 would be less than, let's see, on the right we have 1, 2, 3, 4.5. So 3 is less than 4.5. Another way of looking at this would be that 3 halves is the same thing as 1.5. So actually what we have over here is 3 sets of 1.5 also. That's another way of looking at it. What happened in this context, if we look closely, is that we have the same number of groups. We have 3 in each case. But what's different is the size of the groups. We have ones over here and sets of 1.5 over here. So again, we have the same number of sets, but it's the size of the sets that's different. So it'd be kind of like saying 3 pennies compared to 3 nickels. Now, what if we were to reverse the order? Now, we know from the commutative property that these would be equivalent, but what does it look like when we physically model it? So again, the same understanding. Our first factor is the number of groups. The second factor tells us the size of the sets or the groups. So just like before, we're going to take our given number and compare it to the result from multiplying by a fraction that's larger than 1. And again, for comparison purposes, we change our n to 1 times n, and we're going to let our fraction be 3 over 2 again, which is bigger than 1. And we'll let our number be 3. So we have 1 times 3 compared to 3 over 2 times 3. So what does this look like when we model it? On the left, we have 1 set of 3. On the right, we have, well, let's see, that's just 1 set of 3. That's 2 sets of 3. That's too much. We only need 3 halves, or 1.5 sets of 3. So we need to cut that second set of 3 in half. And so we've done that. And again, comparing, we can tell that our left side is smaller. 1 set of 3 would be less than 1.5 or 3 halves sets of 3. And what happens here is that we have the same sets. For example, let's say these are cookies. So we have 1 set of 3 cookies compared to 1.5 sets of 3 cookies each. So in reviewing this first scenario, again, the distinction in the two contexts was that in the first context, the size of the groups was the same, but the number of the groups was different, as opposed to the second context where we had the same number of groups. It was the size of the groups that varied. Again, in context, it'd be like saying 1 set of 3 cookies is less than 1.5 sets of 3 cookies. In the second context, we have the same number of groups, but it's the size of the groups that's different. So obviously 3 pennies would be less than 3 nickels because, again, of the size of the groups. Now let's look at the second scenario, the second statement, where we're multiplying some number by a fraction that's smaller than 1. So just like before, we're going to compare our original given number to the result from multiplying, in this case, by a fraction that's smaller than 1. Okay, we change our given number to something times 1 for the physical modeling. Let's let our fraction less than 1 be 5/6. And again, for consistency, let's just let our number be 3. So what does this look like? 3 times 1 versus 3 times 5/6. On the left, we have 3 sets of 1. On the right we have, well, let's see, that's too much because that's still 3 sets of 1. We need 3 sets of 5, 6. So we need to take each of those 1s and divide them up into 6 equal parts. But we don't want all 6 parts, we only want 5. So this is what we have. And just using some logic, we can tell that our 3 sets of 1 is going to be more than our 3 sets of 5, 6, because again, the size of the groups is different. You know, groups of 1 are bigger than groups of 5, 6. We could figure this out. We could take some of these 2 shaded parts and put them here and here, and take our unshaded parts and put them here. So we would have 1, 2, and a half. So 3 is bigger than 2 and a half. Just like before, what if we were to reverse the order of our 2 factors? Again, because of the commutative property, we know that they should be equal, but what does it look like physically? So we'll start off with our number. We're going to compare that to the results of multiplying by a fraction less than 1, but this time it's 1 times our number, and let's let our fraction be 5, 6 again. So it would be 5, 6 times our number. And for consistency, again, let's let our given number be a 3. So we have 1 times 3 compared to 5, 6 times 3. So we have 1 set of 3 on the left. On the right, well, let's see, that's too much because that's a full set of 3. That's not what we need. Now, here's something that's a little bit different. Here, it's actually our set of 3 is our whole. So we don't split each one of these up into 6 equal pieces. What we need to do is take our whole set of 3 and split it up into 6 equal pieces. But we don't want all 6. We only want 5 of those 6. So we have that now. And again, just like before, we can look at this and we can actually figure out that this is 1, 2 and a half. So we know that 3 is bigger than 2 and a half. Or just using the logic that we don't have as many of this group of 3 on the right as we do on the left. Putting this to a context, it'd be like 1 set of 3 cakes compared to 5, 6 of a set of 3 cakes. Just like the first context, where we compared the number being multiplied by a fraction larger than 1, we have the same scenarios here. In this context, it's the size of the groups is the same, but we don't have the same number of groups for each. As opposed to this last context where we have the same number of groups, but the size of the groups is different. Again, connecting this to a real-life context, the first context was like a set of 3 cakes compared to not a full set of 3 cakes. And then the second scenario would be we have the same number of groups, but the size of the groups is different. Now let's address the last statement in the standard about relating the principle of fraction equivalence to the effect of multiplying our fraction A over B by 1. Notice that this is unrelated to the first 2 parts because the first 2 parts dealt with taking our number and multiplying it by the fraction A over B. Now, this last statement is actually addressed in standard 4.nf.5b, and there is a Common Core video on this standard. But just to review very quickly, this is the original equation. It would be a little bit easier to interpret if we put this in vertical format. Then we split it up into 2 fractions. And now, of course, we know that any number divided by itself is going to be 1. And so now we know that this statement is true because if we multiply any fraction by 1, we still get the same result. Now, if we were to reverse this process, that's what we would actually do to create a fraction that would be equivalent to our original. So if we start off with some fraction, and we're actually going to multiply it by 1 so that the quantity doesn't change, then we change our fraction to whatever number over itself, depending on what we want to create. And then we just put it as 1 fraction and actually do our multiplication, and we have our equivalent fraction. Now, how is this different from the 4th grade standard? What's different here is that we have to tie this back to that initial statement of interpreting multiplication as scaling or resizing. So what does that look like here? Well, multiplying by 1 and multiplying by n over n, some fraction equivalent to 1, are actually different. They're not the same when you physically model them. Let's look at an example. Let's say our beginning fraction is 2/3, and we multiply that by 1, so nothing changes at all. We still have 2/3. Now, let's look at the second scenario where we have our fraction, and again, let's let it be 2/3, and we're going to multiply it by 1, but this time the 1 is in fractional form, some number over itself. So let's let our n over n be 6/6. So what happens with the physical modeling? Well, now if we multiply it all out, we're going to have 12 parts out of 18 total. So let's look at what really happens here. When we multiply by 1, nothing changes. But in the second scenario, when we multiply by some fraction n over n, we change both the number of parts and the size of the parts. Now notice that we hold true to the multiplicative identity because when we multiply by 1, the size of the whole didn't change in either scenario. But again, we do have some resizing here when we multiply by 1 in the form of a fraction that's equivalent to 1. So there is a difference. There is some resizing in the second context. So it is different. So multiplying by 1 as opposed to multiplying by a fraction equivalent to 1 physically does make a difference. So this standard is important. We need to spend some time on it. It's very important for establishing number sense so that students get a sense of what happens when you're multiplying with fractions. Now the standards don't address the same basic idea with decimals, but if we were to take this standard and substitute decimal for fraction, we would have the same basic idea, that if we were to take a number and multiply it by a decimal greater than 1, we'd get a product greater than our original number. And if we were to multiply our given number by a decimal that's less than 1, we'd get a product that's smaller than our original number. And then looking at the last statement, we would relate the multiplicative identity to where any decimal times 1 would result in the same decimal.